I'm Fernando Pereira from UFMG, Brazil, and today we shall look into different optimizations that apply on programs with loops. The material in these videos has been taken from Chapter 18 of Modern Compiler Implementation in Java, the second edition. Optimizing loops is very important because programs spend most of their time in loops, and compilers contain lots of optimizations that are specific for loops. Today we shall see some of them, but these optimizations will not really change the iteration space of the loop. The iteration space of a loop is the space formed by the product of all the iterations of a nest of loops. But don't worry, this notion of iteration space is not important today. We shall look only into optimizations that don't really change the iteration space, and we shall talk about the iteration space later on in another class. The first goal of today's class is to identify loops. We need to recognize them in the program's control flow graph, but we shall restrict ourselves to a particular class of CFGs, which we call reducible. We shall see what's that today. You might think that identifying loops is easy. Just find words like while and for in the source code. But we are not really working at the source code level. We are working with a lower level representation. So we need to identify loops in the program's CFG. So I have here a program on the left side of the figure, and its CFG on the right side. How can we identify loops in the program's CFG? Would you like to stop the video and think about this question, how to identify loops? You might imagine that a loop is just a cycle in the CFG, and that's right. But in this course, we care about a special kind of cycle that makes up what we call natural loops. A natural loop has three properties, which you can read in the figure. Just stop the video and read it over. But the important thing is that we can imagine that a natural loop is a cycle in the CFG with just one entry point. In other words, there is just one way to go from the rest of the CFG to the loop. And that's through this unique entry point. In the figure, we call it age, the header node. We do not want cycles with multiple entry points, basically because they are hard to optimize. Furthermore, they mostly appear in programs with gotos. If I only have structured code, that is, with keywords like while, repeat, for, and conditionals like if then else, then usually this kind of weird loops never really surface. If they don't exist, then we say that the CFG is reducible. There is a systematic way to tell if a CFG is reducible. I will talk about it, but before I do it, can you tell me if the CFG on the right is reducible? We can keep iterating this procedure on the left side. I'm given an algorithm on the left side, and we shall talk more about it. So we can keep iterating this algorithm to see if we can reduce the CFG to a cycle with two entry points. Basically, we keep collapsing edges. To collapse edges, we join nodes like N1 and N2 if N1 is the only predecessor of N2. Otherwise, if two nodes form a strong component, we can collapse them as well. We keep collapsing nodes until we find a cycle with multiple entry points. Let's see how that works on the CFG. I've simplified it on the right. So, if you want, you can take a look into the algorithm on the left, stop the video and read it over, because now we shall use it as an example. I have painted nodes that we can collapse immediately with the same color. For instance, we can collapse A and B up in the figure because A is the only predecessor of B. On the right, we can see the control flow graph after we have joined vertices with the same color. We keep joining nodes in this way until we find the forbidden pattern, or we can reduce the graph to a single node. So on the left, we join red and blue vertices, thus getting the second graph. We join the red nodes in the second graph, hence obtaining the third. And then we join the red and blue groups of vertices in the third graph to finally obtain the forbidden pattern. Thus, we conclude that the CFG is not reducible. You must be wondering why we don't really like unreducible CFGs. That's basically because they are hard to optimize. Because loops have two entry points, for instance, we end up without a place to hoist invariant code up, for instance. Furthermore, these graphs are relatively rare. Usually they emerge out of very convoluted source code that uses the goto statement, for instance. Like that example that we had seen that was produced by the C program on the right, which uses goto, as you can see, like here and here. So, as a test, let's take a look into the CFGs. Are they all reducible? Or in other words, do the loops have a single entry point? You can stop the video and think about this question. Can you also think about which kind of syntax, for instance, in C, would yield these kinds of programs? And what about the CFG? Is it reducible? Perhaps you would like to collapse some nodes to check it out. You can stop the video, pick up a piece of paper, and then try to find the forbidden pattern. Notice that the only node that has a single predecessor in the CFG is D. So we can join C and D, thus getting the forbidden pattern. And so the CFG is not reducible. And with that, we conclude this first class. We have covered the notion of reducible control flow graphs, and we have seen a little bit of natural loops, but in the next class we shall talk more about this category of loops and how to recognize them in CFGs. Till there, you feel free to write me with questions or comments. Thank you.